Start. Um, there are a few lectures in this course in which I would like to. There is a problem when I'm starting doing a long calculation, and I don't want you to lose the general context, right? It's important to see not only the trees but also the forest. So I will try to stress the points where I'm starting getting into details, and I will make an attempt to clarify the general context in order to avoid you being trapped in sort of one specific mathematical term. Anyhow, fine. So what we are going to describe today. So in the last lecture, we dealt with an example by which I've tried to deliver the main messages of at least of the first part of the course, and now it's time to start working seriously. So with all the respect to polynomial equations like the one we dealt with in the last lecture, as physicists we know that what we are really doing is, in at least 80% of the cases, we are trying to solve differential equations, right? And for the moment we will concentrate on linear differential equations, right? There is a whole science of nonlinear differential equations that by and large I'm not going to go into it this course. So as long as the differential equation is linear, if it's first order, it's solvable, it's an exact equation. And most of the equations that we as physicists encounter are second order differential equations, right? Third order, everything that I will show you from now on have a trivial generalization to third order and fourth order. It's not specific to second order, but I'm going to be focused focus on second order because this is most of the equations that we meet are second order equations. Okay. And as an example, I would like to start with a specific equation, which is an Airy equation, y double prime equals xy. That's the equation. Why I am using this equation as a canonical example? First of all, it's simple. Second, it's non-trivial. Third, okay, if we have no x here, then it's a harmonic oscillator of some kind, right? But with the x is a non-trivial equation. It has actually an interpretation in quantum physics, but forget about that for the moment. I mean, it's just Schrödinger, time-independent Schrödinger equation in a constant constant electric field. You get this. And what's more important is that later in this course we will use it. It will turn out that we are going to use it for some other development. So the Airy equation is going to play around. So it's a good, it's a appropriate choice of an example. Okay. Now, the topic of this and perhaps the next lecture is local analysis. And in local analysis, we would like to study the behavior of a function like this at the vicinity of a given point x naught. That may be 0, may be infinity. Of course, this will be our examples, but it may be every point. Also, right, we want to analyze y of x at the vicinity of x go to x sum x naught. Right? This is our idea, which implies that we have a natural small parameter which is a distance from x naught. So for example, if you want to analyze it close to 0, the small parameter that we have in mind is the distance from 0. Okay? Fine. So here is an equation here, and we want to study its behavior, let's say, at the vicinity of 0. Let me first remind you what you were taught in the, I guess, second year of your undergraduate studies, and we will develop from then on. So the prescription for the analysis of such an equation at the vicinity of 0, say, or in any case, goes as follows. Let's assume, so we don't know a solution for this. Of course, we can say, the solution is any function, right? But I mean, saying that is like saying nothing. We want to some program that will allow us to calculate the values of any function. What is any function of? By the way, there are two independent, of course, this is a second order equation. There are two independent, linearly independent solutions, and they are known as Airy function and Bailey function. There was no person Bailey, it's just the B of Airy, right? And, okay, so how we deal with such a problem? The answer that you were taught back then is to expand, to write y as sum from n equals 0 to infinity of a n x to the power of n, plug it here, and get an equation for the coefficients. That's a general program. Okay, let's do that. Again, now it will involve some complex calculations, but try to defocus from the calculations to see the general picture. So our attempt now is to take this expression and to plug it here. So if this is y, then y prime is a sum from n equals 0 to infinity of a n n x to the n minus 1, and y double prime is a sum from n equals 0 to infinity of a n n n minus 1 x to the n minus 2. Right? And this should be equal to the sum from n equals 0 to infinity.
You need to move the n from 0, n equals 0 to n equals 1, then equal 2.
Why? I took this and I took a second derivative.
Yes, but
okay, this will come. No, don't worry. Okay? And here we have this side, x times y, which is the sum from n equals 0 to 1 to infinity of a n x to the n plus 1. Right? That's it. So this equation is exactly this equation. Just, okay? Now we should say something about the ans. Okay? So in order to, I mean, of course, one can look at this and decide what the ans is, but for me, I can't do that without writing the first few terms. Okay, so let's do that. What are the first few terms of this side? We have here a0x plus a1x squared plus a2x cubed plus blah blah blah. You see? This is equal to, okay, now, the n equals 0 term gives me nothing because I have an n. And the n equals 1 term gives me nothing as well because I have n minus 1, right? So the first term will be a2 times 2 times 1, so 2a2 x to the 0. So it's 2a2. Okay? And now the next term will be a3 times 3 times 3 minus 1, so 6a3x plus a4, so I have 12a4x squared, and so on. Okay? Now I have a sign of equal here, which means that what's on the left is equal to what's on the right. And since this is a Taylor series, it's unique, so we should, the terms should compensate each other for every, separately for every power of x. Okay, so let's start. Let us start. First of all, there is nobody to compensate this. Okay? So there is no other choice, but we must give up and decide that A2 is 0. See? Second, okay, you can see that every term here and every term here involve change in 3 in the index of A. So A0 is talking to A3, A1 is talking to A4, A2 is talking to A5, right? But because A2 is 0, it implies also that A5 is 0 and A8 is 0, so A, it's not only A2 is 0, but also A of 2 plus 3m is also 0. 2, 5, 8, and so on and so forth. They all are zeros. Okay? Good. Next. Now we can start with the coefficient of x. So this was for the coefficient of 1. What about the coefficient of x? We have here A0 and we have here 6A3. So we see that A0 must be 6A3, which implies also that A3 is A0 divided by 6. Okay? Or maybe I will be more okay. What is this 6? This 6 is simply 3 times 2. Okay? Let me write it like that. Right? So I'll write here 3 times 2 times A3, and by the same token 4 times 3 times A4, and so on and so forth. Okay? So this is 3 times 2 times A3. So it's A3 divided by A0 divided by 2 times 3, which is 6. Okay? Now, as we have already, yes, A3 is A0 divided by 2 times 3, right? As we discussed, the A6 will depend on A3, right? Because now A3 here will be the coefficient of x to the 4, and A6 here will be coefficient of a to the 4, right? So we can see, we can even write it, it's the next term. So here we have A3x to the 4, and here we have something that goes like A5 with that we already decided to be 0, plus A6 times 6 times 5 times x to the 4. Right? So this implies that A6 is A3 divided by 6 times 5, which is A0 divided by 6 times 5 times 2 times 3. And so on and so forth. So you see the general pattern. The general pattern is that this is, by the way, one of the solutions. Is a solution that starts at A0 and continue. Right? We will have another solution that starts at A1. We will go to this solution immediately. But let's start with the
You have a marker there.
what?
You have a marker, a blue marker.
Okay, but you see, unbelievably survived the attack. But, So, what we know now is we can write in general that we have a solution which is based on A0, A3, A6, and so on, that satisfies A3, N, right? N is 0, N is 1, N is 2, equals to A3, N minus 1, right? Divided by 3n times 3n minus 1. Okay? And this implies, if we just generalize it, you see A3, A6, that A3n, okay, is A0 divided by 2 times 3. יש איזה תוכניות לעוד טילים בזמן ההרצאה, אני מדבר עם מעין קסם, זה לא הולך ככה. מה זה?
לא, באמת, היום 40 למותו של נסראללה. לא.
כן, זה נכון, כן, היום זה 40 למותו של נסראללה, אבל...
של המוסלמים מה, זה באמת 40? אין לי מושג, אני לא...
כן, יש לזה...
כמו ה-30 יום.
זה דבר, כאילו, 40 זה כמו ה-30 יום, כן, יש איזה דבר כזה, 40 יום.
אצלנו אבל עושים ב-30 יום גילוי מצבה.
תקשיב, כל אחד והמנהגים שלו, אבל
יודעים איפה המצבה שלו.
לא, זה מדהים לחשוב שעברו 40 יום, זה נראה כאילו עבר כבר, כאילו, לא יודע, לי זה נראה שעברנו ממש המון זמן.
זהו, בקצב שהדברים פה משתנים, אתה לא מרגיש כאילו
זה נכון.
התחלפו להם איזה 3 מנהיגים מאז.
מה?
התחלפו להם איזה 3 מזכ"לים.
לזה אתה אבל לא שם לב. זאת אומרת, אם בא בן אדם מחסלים תוך יומיים, אז אתה לא זוכרים אותו.
אז זה גורם לזה להרגיש יותר.
טוב, נמשיך. לא יודע בדיוק, צריך להוריד לוח למטה ולהמשיך את ההרצאה שם.
כל מרצה יעשה את זה, יהיו מלא הרצאות במקביל, שירוצו ביחד.
אתה יודע, בשבוע אחרי ה7 באוקטובר, כן? היו אזעקות מלא. הייתי יורד למטה, בכל הבניין הזה היו איזה 5 אנשים. 5, 8, 10, גג. זה כאילו כל כך מדהים איך פתאום אתה רואה פה נחילים של בני אדם יורדים למטה טוב, אוקיי. חלק מהסטודנטים נתקעו במקלט, אבל נראה לי שאין מה לעשות. אוקיי. So, I continue. I have A3n, so it will be, what I have here is 2 times 3 times 5 times 6 times 8 times 9, blah 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 blah, times 3n minus 1 times 3n. Right? This is how it looks like. Good. So the question is how to simplify this expression. And to do that, we are going to use, again, very important function that will appear many times in this course, and is the gamma function that perhaps you are familiar with, but I think that in the undergraduate studies they do not stress the importance of the gamma function. So, gamma function of x is defined as the integral from 0 to infinity of t e to the x plus 1 or minus 1? Minus 1, I think. E to the minus t dt. And in particular, it satisfies the relationship gamma of x plus 1 is x times gamma of x. Right? This is the importance, which implies, of course, that gamma of 5, say, is 4 gamma of 4, which is 4 times 3 times gamma of 3. Again, I'm using this relationship recursively, and blah blah blah, it's simply 4 factorial. So gamma of an integer is integer minus 1 factorial, right? And however, this product ends because then we have and gamma of 0 is 1. Sorry, gamma of 1 is 1. So gamma of 1 is 1. So and gamma of 1 is 0 gamma of 0. So we don't have any. The product stops at 1. But we are going to implement the gamma function also when its argument is non-integer. In which case the series continues forever. Okay, but still there is a value for gamma. So in order to express these terms in terms of gamma, we are writing A naught divided by, so we have, overall, we have here 2n terms. You see, because we skip every third term. 2, 3, we skip 4, 5, 6, we skip 7, 8, 9, we skip 8, 10, and so on and so forth. Okay, so we have 2n terms. So I will divide it by 3 to the power of 2n, which implies that I divided it here. So every individual term here is divided by 3. Okay? Now what I will get? Let's take only the multiplication. So the 3 will become 1, the 6 is 2, the 9 is 3, and the 3n is simply n. So from all these terms are simply n factorial. Okay? Now, what about the, now let's go to the other terms. The 2 is 2/3 now. The 5 is 5/3. The 8 is 8/3. Blah, 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 up to n minus 1/3. So the challenge is to express this. How to do that? Gamma function. So I'm saying that gamma function of n plus 2/3 is, according to the recursion relations of the gamma function, n minus 1/3 divided by gamma of n minus 1/3. You see? And this will continue now. This will be, so this will be n minus 1/3 divided by n minus 4/3 divided by times gamma of n minus 4/3, and so on and so forth. And I have to continue it until I will get gamma of 2/3. Right? And then I want it to stop. How do I do that? What I would like to claim is that this term is just gamma of n plus 4/3 divided by gamma of 2/3.
Plus 2/3, no? There is n plus 2/3.
N plus 2/3, yes. N plus 2/3, yes. Very much. Yes. So all in all, we find that y of x. So we did find a single solution of this of the area equation. One of the solutions. We have two independent solutions. This is one of the solutions, and this solution is the sum from n equals 0 to infinity of what? Of a naught. The a naught is outside here. I have x to the power of 3n divided by 9 to the power of n. Why 9? Because 3 to the power of 2n is 9 to the power of n, times n factorial times gamma of n plus 2/3. And here I have gamma of what? Of 2/3. Good. This is a solution for the area function. I mean, this is not okay. This is a solution for the area equation. There are two solutions, okay, and I will write you. Okay, let's focus on this solution for the moment. Question. This is an infinite series. For what values of x this infinite series converges?
Positive.
I think about x positive, right. I mean, okay, so actually it also works for x negative, but for what values of x this infinite series converges? to a finite number. We have seen in the last lecture that sometimes we can write an infinite series, but it does not converge if x is large, too large,
X
right?
smaller than 1.
Okay. So how we think about such a problem? We want to say as follows. The gamma function is, you know, some sort of a factorial. When n is large, okay, it will behave like n factorial. Gamma of n is like n factorial, right? It's not exactly n factorial because it's not an integer, but the gamma is continuous between the integers. So it's more or less n factorial, okay? Now, what we will have here, so, and gamma of 2/3 is a number, it's pi over 6 or some garbage like that. What?
It's a constant. It
Yes.
doesn't matter.
So, what we have here, we have actually, if you just want to ask whether or not the n terms for large n blows up. Okay? So how the n terms looks like here? We have x to the power of, or I want to write it as, yes, x cubed over 9 to the power of n, right? X cubed over 9 to the power of n. And here I have 1 over n factorial squared. Okay? This is how this expression behaves for large n. Now what we have here, let's take the 9. Okay. Clearly, if x cubed is smaller than 9, okay, then everything gets smaller and smaller and smaller as n increases.
Even if it's equal to 9.
Wait, if x cubed is smaller than 9, then I have here something which is smaller than 1, and as n increases, both this term becomes exponentially small, and we have also another suppressing factor here, so it will go to 0, no depth. However, even if x cubed over 9 is very large number, we still have, what we have here is an exponential growth, right? Because we can write it as e to the n times the logarithm of x cubed over 9. So whatever number it is going exponentially with n. And you know that n factorial is going faster than exponentially, right? And n factorial squared is going like the squared, a squared bigger than, okay, so it's much faster than n exponential, which implies that this will go to 0 as n goes to infinity no matter what. For every x, no matter how big x is, this series will converge. Right? Which implies that the A function is an entire function. Yes, the power series converges for every x. Yes.
If the terms converge, it doesn't necessarily mean that the series converge. For example, 1 over n, the terms converge.
No, it falls down much faster than the whatchamacallit, the harmonic series. It converges. No doubt. Okay. So this again, this expression converges for every x. Okay. However, convergence is one thing. You know, mathematicians that have shown that this converges for every x. For them, this is enough. We define a function. Here is a function, right? For us physicists, we have another task, which is to calculate the damn function. And to do that, the question is now, how many, so I can't take infinite number of terms. I can take only 10 terms, maybe 20 terms. Maybe I'm working with a computer, so I will take a million terms. Still, how many terms I should take in order to reasonably converge to the right answer, right? And it turns out that the convergence here, of course, when x is not small, is not so fast. Yes, so you have to take, 10 terms in order to calculate it with reasonable accuracy up to x equal 2. Right? So, okay, but in principle this is the answer, and I will, for the record, I will not make the derivation of the other. We said we must have two independent solutions, so this is one of the solutions that comes from 0, 3, and so on, and we have another solution, let's call it A1, which comes from n equals 0 to infinity, x to the 3n plus 1, divided by, and you are invited to make the calculation, and this will be again 9 to the n. Here we have gamma of 4/3. That's why I wrote 4/3 before, because it confuses me. And here we have gamma of n plus 4/3, I think. 1/3 maybe. Okay. Check. 4/3. Times n factorial. Yes, these are the these are two independent solutions for the area function, and they converge, and everything is nice. Just one remark. When people, I told you that the answers that you can find in books are called Airy and Bailey, right? And the Airy and Bailey, you may have think that this is Airy and this is Bailey, or vice versa. But no, every linear combination is also a solution. And just for to be right, Airy is these solutions with A0 is this solution with A0 3 to the minus 2/3, and B and A1 is minus 3 to the 4/3. Whereas Bailey comes with A0 3 to the minus 1/6, and A1 which is plus 3 to the minus 5/6. This is, I guess, minus 4/3. Yes. So these are the Airy and the Bailey. Why people have chosen these weird coefficients? Of course, it's a choice, because again, every linear combination is a solution. We will understand it later today. Good. Fine. So this was an example, just to remind you what you actually did in your undergraduate studies. Also, it helps by reminding you what the gamma function is, but this is essentially essentially the story. And now I would like to return from this example to the general theory. So, by and large, we consider now a second order differential equation. That's it. Okay, a homogeneous and linear second order differential equation. So we have an equation of the form a of x y double prime plus b of x y prime plus c of x y equals 0. Okay, homogeneous and linear second order differential equation. this is our example. What I will tell you now is completely general for equations of any order, provided that they are linear. Okay, the general theory of linear differential equations, not only second order. So, and I want to analyze the behavior of this function around x some x naught. We have a point x naught in the complex plane. So this is real x, and this is the imaginary part of x, and this point is x. I want to analyze the behavior of this equation around x naught. What we can say? So first of all, let me make my life easier by dividing everything by a of x. I can do that, right? So I will end up with this will be a of x and this will be b of x. Now, option number one. Both a of x and b of x are analytic at x naught. Both a of x and b of x are analytic function at x naught. If this is the case, then we have a great theorem by Mr. Fuchs. And first of all, the name of this case is an ordinary point, OP. Ordinary point, a point in which x naught is an ordinary point if a of x and b of x are both analytic at x naught. In this case, Mr. Fuchs worked very hard to give us a guarantee that we have two solutions, both of them of the form y equals sum from n equals to infinity of a n x to the power of n, that converge to the correct solution, and the radius of convergence is at least the distance to the next to the next singular point, right? So if the closest singular point is here, say, then the radius of convergence is at least this one. You see? And I just want to mention that any function is indeed, so any function, for any function, what is a of x?
0.
0. What is b of x?
X.
X. And since x is an entire function, any function the functions may be expressed in this way, and the series will converge for any finite x. This is exactly the definition of an ordinary point. Okay? Are we on the same page? Good. Next type is, this is type number 1, ordinary point. Next type is, type number 2 is regular singular point. Okay? The name sounds self-contradictory, and it is indeed not a nice name, not a good choice of a name, but this is a name, regular singular point. Regular singular points implies that either a of x or b of x are not analytic at x naught, but a of x times x minus x naught or b of x times x minus x naught squared are analytic. You see why this is squared, right? This is a of x. This goes like 1 over x. A of x, and here I have 1 over x, so I multiply it by x minus x naught, and this is b of, you see, okay? And you can generalize it to any order if you like, right? But so either a of x or b of x are not analytic at x naught, but these functions are both analytic. You see? In that case, Mr. Rovinius told us that we may have at least one solution of the form sum of from n equals 0 to infinity of a n x to the n plus alpha, right? There is some, I mean, alpha should not be an integer. And the second solution either will have this form or will have the form sum from n equals 0 to infinity of a n x to the n plus alpha ln x. Okay, this is irregular singular point. Now, and this is because these are Rovinius series that you have already encountered again during your undergraduate studies. And since I hate regular singular points, I asked the instructor to give you an exercise about that, and I simply skip it and continue to the third type of point. Okay? So points of the third type, this is first type ordinary point, second type regular singular point, and the third type is irregular singular point. Now at least it's self-consistent. The name is self-consistent. And in an irregular singular point is every point which is not neither that nor that. Right? So every point which is not ordinary point and not regular singular point is an irregular singular point. Fine. Now, what about the area function, area equation? Which point? So we say that in every finite x, right? X is an entire function. So in every finite x, a of x is 1, and it's analytic everywhere, and b of x is x, and it's analytic everywhere also. So we can always approximate it this way. Not approximate, I mean expand it this way. However, there is one point in which this is not true. Where? In which point a function becomes, which point is the irregular singular point of the area function? No other choice. X goes to infinity. Right? So to analyze the behavior of a function when s goes to infinity, when x goes to infinity, we have to make a change of variables. We will define x as 1 over t, so t is 1 over x. Okay? And therefore, ddx is d dt dx. But what is dt dx? Is minus 1 over x squared. Okay? But x is 1 over t. So dt dx, okay, so I have here minus t squared ddt. Right? It's d dt, dt dx. Dt dx is 1 over x, minus 1 over x squared, and x is 1 over t. Okay? So this is d dx. And what will be d2 dx squared? I have to take this operator and act on itself. So I will have, first of all, I will have t to the 4 d squared dt squared. And then we can work with the ddt on the minus t squared, and this will give me plus 2t cubed ddt. See, this is what I get when I work with this on itself. You see that? Okay? So what is any function in terms of t? Any function is in terms of t will be t to the 4 y double prime. Y now is a function of t. Okay? So t to the 4 y double prime plus 2t to the 3 y prime. Right? This is something that I don't have in the original. I don't have a first derivative, but now after the change of variables I will have. And now I have minus y over t. This is the xy equals 0. And if I divide everything by t to the 4, in order to have 1 in the coefficient of the highest derivative, I will have y double prime plus 2 over t y prime. This by itself will be at t equals 0 irregular singular point, because it diverges, but if I multiply it by t, it does not diverge. Right? And I have another term, minus 1 over t cubed equals 0, and there is no q to this term. So this term, as t equals 0,
not q, to the 5.
what? To the 5. So, right? This term, as t equals 0, it diverges, and if I will multiply it by t squared, right, it still diverges. So the Airy function has an irregular singular point at infinity. Okay? Good. Now, as I told you, there is a very nice mathematical theory for solutions of equations or series expansion for equations close to an ordinary point. And there is also quite annoying theory, but still something that one can prove for the behavior at the vicinity of a regular singular point. At the vicinity of irregular singular points, there is absolutely no theory at the level of Fuchs and Rovinius, and all we can do is to improvise. Right? We have to, to stare at the equation and to guess what we should do, because close to irregular singular point, the function is doing horrible things. It eats babies. It does all kind of crazy behaviors, and there is no good series that will take care of it. So we have to think what to do. Okay, and actually the main the topic of this talk was supposed to be what to do when you have an irregular singular. Okay, so first of all, let's try to get some intuition. How do I get an intuition? I will get it from looking at irregular singular points. At irregular singular points for first order equations. So for equations that I know how to solve. Okay? So let's make a comparison between 3 cases. And I hope that this will give us a kind of intuition. Right? Case number 1, y prime equals y over 2. Oh, should I do it with a minus? Whatever. Y prime minus y over 2 is 0. Okay? This is an first of all. At x equals 0. X equals 0 is what type of point? Ordinary, regular singular, or irregular singular? Ordinary point. X equals 0 is an ordinary point. You see, we have here just 1/2, and 1/2 is a constant, so it is analytic close to a to 0. So at the vicinity of x equals 0, this is an ordinary point. Okay? Now, but we can solve it without, right? We can solve it by just saying that dy over y, this is an exact equation, right, is equal to 1/2. Okay, let me write it with a plus. Okay? Which implies that y is, so ln y is minus x over 2, which means that y is some constant a times e to the minus x over 2. Okay? This is how the function looks like, and then now we can understand how the Taylor series will look like. It's just an expansion of e to the x minus x over 2. Good. What about, so this is an ordinary point. What about the equation y prime plus y over 2x is 0? Okay, okay, I must, okay, first of all I must explain how the criterion for regular singular point have, what is the criterion for first order equations, or second or third. This is for second order, right? And the idea is that you multiply, if you start with y to the nth derivative of y, and a is the coefficient of the nth derivative of y, right, a of x, then you want a of x times x minus x naught to the power of n minus m to be analytic, right? And you can show, you can understand this is a is a, here m is 1 and n is 2, and here m is 0 and n is 2, right? So here n is 1 and m is 0, okay? So you see that if I will multiply this by x, it will be analytic. So this is regular singular point. This is an example of a regular singular point. Okay? Of course, but what I'm doing, I don't need to have Frobenius series here because I can solve it immediately. And you see that this implies that dy over y is minus 1 over 2x, which implies that ln y is minus 1 over half ln x, which implies that y is a times the square root of x. As I told you, in Frobenius, you have an alpha which is not necessarily an integer. So here, you see, here if you expand it, you get something with integer powers, and here it starts with square root of x, which is alpha equals 1/2.
You can take a Taylor series square root of x.
Of course. Yeah, also here. I mean, the x to the alpha is sitting here. You are not expanding this. You're expanding the rest. Now there is no rest. Okay. Now what's happened if we have irregular single? Okay. Now let's speak about y prime is equal plus, sorry, y over 2x squared. Because there is an x squared here, even if I multiply it by x, it is still singular at 0. So now 0 is an irregular singular point, but I can still solve it because it's an exact equation. So I can write that dy over y is minus 1 over 2x squared, which implies that ln y is the integral of this garbage, which is 1 over 2x, which implies that y is a e to the 1 over 2x. Should I have a minus here? No, I think it's a plus. Anyhow. Okay? Whatever. What?
No minus.
No minus.
From the integral.
Yeah. So what you see here is why the irregular singular point is so bad. Because you see, the function is going to infinity in the most ugly way. Like e to the minus 1 over x. E to the 1 over x. So when x goes to 0, 1 over x goes to infinity, and this is going exponentially fast to infinity. Okay, so it's, I mean, the function gets crazy close to an irregular singular point. I mean, it is doing something over. Good. What?
At least there's the 2.
Yeah, but okay, but and this is typical, right? In some other cases, we will get here minus, which implies that the function is going to 0 in a horrible manner, and of course there is no expansion. I mean, this is an essential. Here at x equals 0, we have an essential singularity. We have no expansion whatsoever around 0. Right? This is a feature of an irregular singular point. There is no way to expand it around. There is no way to expand it around an irregular singular point. Good. So up to now, so if now I'm asking you what I should say about the area function as x goes to infinity, your answer, after all this propaganda, I guess that your answer should be, forget it, find another problem to deal with, because infinity is an irregular singular point and it's a lost cause. You're not going to see anything in your life. Fortunately, a few smart guys have analyzed this problem, and it turns out that to understand what is going on when x goes to infinity, for us physicists, is much easier than to understand what is going on close to 0. Because close to 0, we have to work hard to write this power series, and then we have to sum term by term, and we sum 10 terms, and it goes up to x equal 2, and maybe if we sum 100 terms, it will be good up to x equal 5, and so on and so forth. It's very difficult work. Now we will see that the local analysis around irregular singular points, so this is what we are going to focus on from now on, is the analysis of equations, of differential equations close to irregular singular points. Okay? Are you with me? Again, I hope that the calculations are not hiding the message. So, good. So here is the trick. Here is we have area equation, as I mentioned, right? We have area equation which is y double prime equals x y, and I want to analyze it as x goes to infinity. That's my goal. First trick, I'm going to write y as, or maybe I will write it here. I'm going to write y as e to the s of x. Is that a problem? No, because I didn't specify s. So every function y may be written that way. The only problem is that I have to specify s.
S can be complex?
Can be anything. Okay. Which implies that y prime is s prime times e to the s, which is s prime times y, and y double prime will be what? Okay, now I can take the derivative of the s and get s double prime. Or I can take the derivative here and I will get plus s prime squared, right? Both of them times y, which is e to the s. So I can write this equation, instead of writing it for y, I will write it for s, and I will get s double prime plus s prime squared equals what? X, because y cancels out.
It's like in WKB, right?
Yes. It's a cousin. WKB is a cousin of what we are doing now. And yes, there are. If you know WKB, then you can immediately write the answer, but I want to explain what is going on. Good. Is that equation easier than this one? No. Why not? Because there is the law of conservation of hardness saying that by looking at something like that and like that, it is not going to make your life easier, right? So if this is not solvable at x goes to infinity, then this is not solvable as well. The only new thing that I introduced here is that we have nonlinearity in the equation, which is, you know, the raw thing you want to have in your equation. Okay. So, and now comes the big trick. We take the trumpet, right? And the big trick is so now I don't want to find s such that s double prime plus s prime will be equal to x. I want to find s such that s double prime plus s prime will be asymptotic to x at x goes to infinity. Of course, we cannot say asymptotic to x without defining where it should be asymptotic. So at x goes to infinity. Okay? Which means that I want that the division of this by that as x goes to infinity is going to 1. Okay? So this very small change makes our life fantastic. Why? Because now we can implement the other trick that we have mentioned last lecture, which is doing dominant balance. We have 3 terms, and we guess that when we take x to infinity, one of them will be negligible, and the 2 others will cancel each other. Right? It may happen miraculously that all the 3 are, one of them is half, one of them is half, and the other is 1. But unless such the devil is coming and making our life harder, we expect only 2 of them to be important as x goes to infinity. Now, how do we decide which are the 2? We want to decide it self-consistently, the same way we did in the last lecture, right? So there are 3 options. We can believe that we may believe that this term is negligible. That's a purple strategy. We may believe that this term is negligible. That's the blue strategy. And we may believe that this term is negligible, which is the green strategy. Right? So the blue strategy implies s1 squared is asymptotic to x, and s double prime is negligible. Okay? The green strategy implies, this is the blue strategy there. Sorry. The green strategy implies that s prime squared is asymptotic to x and s double prime is negligible. And the purple strategy is that S double prime is asymptotic to S prime squared. Why with a minus sign, right? Why I move it to the other side? Because nothing is asymptotic to 0. As I told you last time. Any comments, complaints?
That can't be the blue ones, they rigged the elections.
What?
It's not very relevant.
Okay. So, let's start with the blue strategy. Okay? Blue strategy implies that S double prime is proportional to X. This implies that S prime is going like what? Like the integral of X. Which is what?
X to the power of 2.
X squared over 2. The 2 is not important, but it is going like X squared. Right? And this implies that S prime squared is going like X to the 4 over 2. Clearly, as X goes to infinity, X to the 4 over 2, the S prime squared that we have, no, I use the wrong colors. Sorry. I use the wrong colors. The blue strategy is S prime squared goes like X because I neglected the blue. Then we have the green strategy of S double prime is going like X, and we have the purple strategy of S double prime is proportional to minus S prime squared. So, okay? So, so we have analyzed this strategy, the green strategy, right? Not the blue, or the green. And this implies that, as you said, that S prime is proportional to X squared over 2, which implies that S prime squared is proportional to X to the 4 over 4. And clearly, when X goes to infinity, this will be much larger than X. And much larger than S double prime, because S double prime is going like X. So this is not self-consistent. You see? I mean, this is a very important point. Please make sure that you understand it.
How we went from two derivative to one derivative? I mean,
integration.
Okay.
The integral over S double prime is S prime. Okay? So, with all the respect, we have to prohibit this strategy. Okay? Next, let's go to this strategy. This is S double prime is going like S prime squared. Yes? What does that mean? That means that, okay, let's call S prime Q. Right? So what it tells me is that Q prime is going like 1 minus Q. Right?
Square.
Minus Q squared. Yes. And this implies that Q is going like 1 over X. Right? Because the Q over Q squared is going like the X. So Q is going like 1 over X. Which implies that S is the integral of Q. So the integral of Q is going like ln X. Right? So if S, okay, but we have to compare. Note that we have to compare S double prime or S prime squared with X. Right? So Q S prime is 1 over X. Q is S prime, right? S prime is 1 over X. So X prime squared is 1 over X squared. And clearly, S double prime will also be 1 over X squared, because otherwise they will not balance each other. But clearly, X is much larger than 1 over X squared when X goes to infinity. So again, we have to abandon also this strategy. And what remains is this. So this must work, because there is no other choice. Something should balance asymptotically at x goes to infinity. Now this implies that S prime is going like plus minus square root of x. And so S double prime is going like plus minus 1 over 2 square root of x. And just for the record, S is going like the integral of that, so it's plus minus 2/3 x to the 3/2. Just integration. Okay? And this is consistent because S prime squared is going like x, and the term that we have neglected, which is S double prime, right, that we assume to be negligible, is indeed negligible because it is going like 1 over 2 square root of x. So with respect to x, it is going to 0 when x goes to, as x goes to infinity. So this is the correct strategy. Actually, it almost always happens just as a, I mean, of course you can do this dominant balance consideration every time, but it almost always happens that the S prime squared is a correct term to take, right? There is a reason for that I've forgotten to, I mean, during the years. Yes?
That can be the x sometimes?
What?
That happens to be the x in some cases?
No, I mean, it always happens that S prime squared is much larger than the S double prime. Right? Because you have the e to the 1 over x. You have to think about the solutions that I've shown before and to convince yourself that this is indeed the case. In any case, okay. So, having that, we can apparently we now have a big victory, because now I know how y behaves as x goes to infinity. What I know that y is e to the s, and s is asymptotic to this when x goes to infinity. So I can say that y is asymptotic to e to the plus or minus 2/3 x to the 3/2 as x goes to infinity. Fantastic. In a single line, work of 3 seconds once you know how to do that, right? No expansion, no consideration of an is going like a 3n divided by 72.3. No gamma functions. Here is the behavior, right? This calculation, the name of what we did now was we have calculated the controlling factor. This is the controlling factor. However, okay, now this is true. There are many physicists that when they have to calculate something like that, they calculate the controlling factor and run to publish the paper. Right? No problems. However, I must, because this is a course of mathematical physics, so we have to give some respect to the mathematics, I should tell you that I have lied to you. Why? Note the following point. S is asymptotic to Z. Does that mean that Y, which is e to the S, is asymptotic to e to the Z? You see? We have a general question here. Suppose F is asymptotic to G as x goes, everything as x goes to something, right? This implies that the limit when x goes to x naught of f over g is going to 1. What can we say about e to the f asymptotic to e to the g? This was what I did. You see? This implies that the limit of e to the f minus g as x goes to x0 is going to 1.
Won't work because you don't have
Which implies that f minus g, right, that the limit of f minus g as x goes to x0 is going to 0.
I think the mathematician proved that the e to the x is a uniformly continuous function, and then you can say that this
I showed you that, I mean, it's a very simple calculation. This is definition of asymptotically equal to, okay? And when I'm trying to implement it to the exponents of both functions, I'm getting e to the f divided by e to the g, which is e to the f minus g. And in this will go to 1 only if f minus g is going to 0. So if the difference between f and g is 1 over x, and x goes to infinity, then it's fine. But if the difference between f and g is ln x, and x goes to infinity, then it's not fine. Right? Even though where this is satisfied, this shouldn't be so. It is not necessary that this implies that. This implies that only if f minus g goes to 0 as x goes to infinity or x goes to x naught. Okay. So in order to so saying that, you see, saying that this implies that is a jump that we have to justify. Right? As I told you, many people are calculating the controlling factor and are going happily to their homes and publish papers and everything is nice, but between me and you and other people, it is not necessarily true mathematically. Okay, so what we have to do, we have to calculate somehow what is the difference between S and this. Right? You see what? Okay, I will. If S is 2/3 x to the 3/2 plus 1 over x to the 4, then S is asymptotic to this as x goes to infinity, and also I can do this.
נדב, המיקרופון ב...
מה, מי?
לא עובד.
עכשיו אתה נזכר להגיד את זה.
יש ביוטיוב,
אתה היחיד שם, אולי.
ביוטיוב זה לא משנה בכל מקרה.
Okay, בסדר? However, if what is written here is the logarithm of x, right? The logarithm of x is not going to 0 as x goes to infinity, so we cannot write this. We have to take another thing. Okay, so what we are going to do, we are going to return to this equation. Okay, I will take extra 5 minutes for to compensate for the silence. Okay, just to end up. Okay, now let's write as follows. We started with s double prime plus s prime squared is asymptotic to x. Okay, now I want to write s will be this plus a function d. S prime will be this plus a function d prime. S double prime will be this plus a function d double prime. And I want to calculate d. Okay? All I know is that D is negligible with respect to x, right? That D is negligible with respect to x to the 3/2 at x goes to infinity, and so on. D prime is negligible with respect to square root of x, and D double prime is negligible with respect to 1 over square root of x. See? So what I will write here is as follows. I have S double prime, which is plus minus 1 over 2 square root of x plus D double prime, plus S prime squared. What is S prime squared? S prime squared is x plus minus 2 square root of x D prime plus D double prime,
D prime squared.
D x plus D prime squared, yes. Okay? All this must be equal to x. Now, this x and this x cancels out. This is actually what we did in the last step. Right? And we can also say that we can also say that D prime is negligible with square root of x. So this is much smaller than that as x goes to infinity. And D double prime is much smaller than that, so we take that out. All in all, what we find for D is that, note that plus minus are the same. So 2 square root of x D prime is asymptotic to 1 over 2 square root of x as x goes to infinity, which implies that D prime is going like 1 over 4x, which implies that D is 1/4 of ln x. Okay? So you see that indeed the difference between S and this is something that is not going to 0 as x goes to infinity. And we have to include it. We have to, I have a minus here, I guess. Right? Yes. I move it to the other side. Okay? So what I have here is that S is plus minus Z plus minus, 1/4 ln x. And if we plug it here, we find that as x goes to infinity, y is proportional to x to the minus 1/4 times x. Okay? So we have calculated the second term. Is that enough?
Now you need to check that this one.
I have to check to continue the calculation, and to check that then I have now to add here, D prime, D double prime, and now I have to add f, I don't know, and to check that f is indeed something that is going to 0 at x goes to infinity, like 1 over x. Trust me for the moment that this is the case. Right? And this is usually what's happening, that we have to calculate only the first 2 terms. Calculating only the first term is, technically speaking, finding the controlling factor or doing geometrical optics. It is equivalent to geometrical optics. And finding the second term is doing physical optics.
Wave optics?
I've forgotten the name, but yes. Okay, and then there are other terms. Of course, we can continue this process forever, but the other terms are negligible at the limit x goes to infinity. So this is a true asymptotic relationship. Right? So this is the behavior of the Airy function as x goes to infinity. And you see that we have 2 types of Airy functions. One of them that blows up as x goes to infinity, when we take the plus here, and one of them that goes to 0 horribly fast when x goes to infinity, which is the one with the minus. The one with the minus, and this is why the coefficients were chosen the way that I have showed you they've chosen. The one with the plus is the Bailey, the one that diverges at infinity, the one that converges at infinity is the Airy. That's why they have to choose the coefficient like that in order to have one of them that blows up, and one, of course every combination, other combination will blow up, because if you add something, the Airy to the Bailey with whatever coefficient you have, then it will blow up to infinity. So to distinguish between the two behaviors, they took coefficients such that one of them is pure plus and one of them is a pure minus. Good. So unfortunately, I wanted to do much more in this lecture, but okay, we have the sirens in the middle. This is what we did, and we will continue from this point next week.
I didn't look on the time. I need to start. That were just asymptotically solution. How do you solve it? Do you solve things like that? I still have to do the the part on variation method. I will ask, there is no one on Zoom, so I will ask you, do you want me to do one example of variation method, or are you feeling comfortable with it? Because I already uploaded the homeworks. So you want that? Okay, we'll do that. That is no problem. That will be very quick. We will cover it very quick. It's not that hard. So variation method. Let's start. Variation method. The idea is that given two solutions to the homogeneous equation, so I will note that as homogeneous, just to write it short, YH1 and YH2. Okay? Now we want to solve ODE in the form of y2 primes plus p of x y prime plus q x y equal to g of x. Be careful. The coefficient of y2 primes has to be 1. In the homework, by the way, I gave you generalization of the variation method to higher order of differential equation. I gave you a method that with that you can generalize it to the nth order. If you know how to solve the second order, you can solve the third order. If you know how to solve the third order, you know how to solve the fifth order. The only thing that you have before is a number of homogeneous solutions, like the order of the differential equation. The same number, right? Because there is, if you have nth order differential equation, you have n solution to the homogeneous differential equation. Everything is linear, just just to verify that we're talking the same language. Okay. So what the variation method say is, okay, the idea is the non-homogeneous term is in the form of u1 of x y h1 plus of x plus u2 x y h2 of x. From here you add an ansatz that if you will take the derivative on u1 and u2 and multiply u1 tag with y h1 and u2 prime with y h2, it will be equal to 0. Why I can do that? Because I add 1 degree of freedom, right? Because I assume there is 2 general functions here. And I'm choosing u1 and u2 such it will obey that ansatz, and also that this thing will be the solution to the equation, this equation. And with that ansatz, that is actually the smart idea here, I can get that u1 is equal to minus the integral of y2 g y2h g of x divided by the Wronskian on yh1 yh2 dx. Okay? And u2 supposed to be yh2 g of x divided by the Wronskian of yh1 yh2 dx. Right. By the way, if I will switch yh1 and yh2 from the symmetry of the equation, it's supposed to give me the same thing, but the only thing that will change is u1 and u2. u1 will become u2 and u2 will become u1. So why this thing happening? Because you look here, there is minus sign. So someone know? Wronskian. And a quick way to see that is because the Wronskian is the determinant, and switching that is like switching the columns in determinant. And from determinant rule, we know already that becomes with minus 1. Therefore, if you will switch 1 and 2, you will get another minus sign from that, and then everything is fine. So it's just sanity check, right? Okay, so now we can do a little bit of exercise, variation of parameters. Let's look, wait, where is that? Okay, let's look on equation, now with equation 2 in tutorial 1, but it's okay. X squared I 2 primes minus 3x y 5 plus 4. Okay, that is the equation. First thing that you need to check What is the first thing? Homogeneous solutions, and before that, okay, actually that is the first part. You read it here. Find homogeneous solutions. That I assume everyone know we did already in last tutorial, right? We actually think solved that equation, and we got that the solution you plug and you set y in the form of x to the r, and you get from that characteristic polynomial that in that form. Therefore, what is the solution? General?
X to the r.
X to the r, here it's x squared plus x squared ln x. Right? Just to remind you from where the ln comes, if you assume there is a little bit of perturbation here, 2 plus alpha, where alpha is very small, the first term of x to the alpha will go like that, alpha ln x. And then, because obviously I forgot to add the constant, we don't care about constants, just the behavior. That is another solution that were hidden. Okay. So we find the solution. Now what we're doing, we have two solutions. You can check that the Wronskian is not equal to 0. And I will tell you the Wronskian is actually x to the third. Someone can check that. It will be great. Yes. Everyone know how to calculate the Wronskian? Someone need to do that? Very good. Because I don't want to. Okay.
Then now I want you to.
Go away. Okay. And from here,
Should it be
it's
minus
just
there?
what?
Should it be minus there?
Should it be minus there? You're just trolling? No.
Yes.
So what we're now doing is just plug into the formula, and like every TDS part in ODE regular course, you just calculate the integral. I will do that because I want to show you a little bit of a trick to do those kind of integrals. That can be very helpful, and later on in the course will give you actually a nice way to do most of the stuff.
But first you need to
Wait.
change the equation itself, so it will be standard, or it will be in the standard form.
You need to divide both parts by x squared.
Yeah. I will do that. That is not a problem. We did it here. Do it also here. That
Okay. So now
yeah. Okay, that is not a problem. Now let's plug just U1, and from here I will stop because I don't see the point of doing that. Actually here my trick is not that helpful, but in most cases it will be very helpful. Okay, I will present it. It's a different way of doing that. In our case, it will be very dumb to do it in that way. But I will do it. I will calculate that integral that comes from, let's call y1 to be x squared because I like the simple case, and let's do it.
Minus.
No,
Minus.
if you walk in y1, it's u2.
That is
No.
y1,
No.
u2. Yeah, because I want to plug in y1, like here.
Oh, yes.
Okay, that doesn't matter. Okay, so obviously, what is the derivative of ln? Ln of x? 1 over x. So here it's very easy to get the integral. It will be just
Tan, nine.
1 square over 2.
ln squared over 2. Right. But we actually have a nice trick to do when we see ln. It's a little bit in that case there is no need for that, but let's do it. Let's do it because it's nice. You will use that a lot when you do some approximation and you have ln. If you have trigonometric stuff and exponents and all of those stuff, you will use that. So we know that if we set alpha to be a small parameter, okay, we know that ln of x is actually approximately x to the alpha minus 1 divided by alpha. And now, dealing with monomials is much, much easier. Okay, here if you didn't show that the derivative of ln is 1 over x and then you see that, you can actually do some brute force of that and find the solution. It's a very nice way of doing things. Okay, so let's do that. At the end, we have to take the limit of alpha go to 0, right? It's like doing the derivative with respect to alpha of x to the alpha. Okay, so let's plug that. We have 1 over alpha outside, x to the alpha minus 1 minus x to the minus 1. Let's call that 1 over x. And then we get from the dx that 1 over alpha, here we get 1 over alpha squared x to the alpha minus, we have here is another thing, no, I don't think so, ln x, yes,
1 over alpha.
1 over alpha, right. Another thing, need to check. Yeah, I think I'm right. Okay, so here we will have to take another, we will set that to be alpha ln x, and we will have to take another term. Do I have another? Okay, it's up to a constant. What?
How did you get this approximation with alpha?
Alpha x to the alpha minus 1 divided by alpha.
Yes.
If you will look at x to the alpha, what would be the derivative with respect to alpha? By the definition.
Alpha.
Let's look at that like y, and then alpha is at 0.
Ah, okay.
So from definition, it's just plug in. Look at that as a function of y, and take the derivative. So what you will do is, let's set that to be f of y. So you plug in alpha minus f0 divided by alpha, right? And then take alpha to 0, then you will get the derivative. So the derivative is actually ln x to the y, and we want that at y equal to 0. So at y equal to 0, it will be equal to ln of x. So from the definition of the derivative, we will get the same thing. Do you see that? Yeah, it's just a nice way of doing things. So let's go. You understand? Okay. And now if I didn't, yeah, I think it's right. Let's write that from 0 to t. 0 to t, just to get rid of constants. You will see why. You have to do that on specific integral. You can't just do it on a general integral because then it will be up to a constant. That constant can depend on alpha and then it will explode. So you need to be careful. Here we do that. And now we take up to second order because we have 1 over alpha squared. So what we will do is, am I too slow? We can speed up. Okay? But you divide by alpha squared. That thing. So what you actually get is the constant you just can get rid of. You can get rid of. Why? Because you have 0 to t. Right? Everyone agree with me? Alpha ln x is just 1 over alpha ln x. 1 over alpha times ln x. Let's be correct. And then it cancels with that thing, right? And then the alpha here and the alpha here canceling out, and what we get is ln x squared divided by 2. So it's very nice. It's actually even nicer to do it on example like that. Here will be much nicer. Okay, of course you can do integration by parts, but when you will have some sinus and a lot of those stuff, it will be just horrible to do it in other ways. So when you just want the asymptotic, it is excellent. Sometimes it can provide you with the actual solution if you do it properly, taking alpha to 0, right? Understand? Okay, so we did what I promised you from last week, do the variation method. It's pretty much nothing, just doing integrals. It's Calc 2, right? So everyone should already be a master of those stuff. Now let's go to the second tutorial and let's talk about ordinary points, regular singular points, and irregular singular points. So let's just give the definition and then I will talk only about regular singular points because ordinary points and irregular singular points we already talked in the lecture. Next tutorials, I think we will just focus on irregular singular point because that is the really interesting. It's more interesting than regular singular point because you already have a recipe how to solve every question in a regular singular point. You need to identify it and then Provenius, if you remember from OD class. So that's why we only talk about that. in this tutorial. But irregular singular point, it's real art. There is no recipe to how to solve that, and in most cases you will have similar methods, but there is not really a way, and you can only approximate the solution. You can get a very good approximation actually. I think you already saw at e to the s, right? That will be the main thing. But okay, so ordinary point. Okay, before that, let's set the equation. For now, I'm talking about equation in the form of y2 primes plus q of x y prime plus q of x y. Okay, now we are only talking about homogeneous equation. Why?
Because we know
Because we know how to find the particular.
Yeah. If I know the homogeneous solution, I know everything. Pretty much so that if I have all the homogeneous solution, from there it's just to do some integrals and you find what you need, the non-homogeneous term. But so non-homogeneous ODEs are not interesting, because if you know how to solve the homogeneous ODE, is when it's much easier and nice form, you know how to solve that. So okay, now ordinary point OP. What is the definition?
Of P of X and Q
If
are analytical at the
Yeah,
vicinity we want. At the
let's
point
write it fancy. P and Q are in C1. What is C1?
Continuous differential equation.
Yeah, you can take the derivative and it will be still continuous. Actually, because it's second order differential equation,
C2.
we actually need C2 at least. But for now, just to say it's ordinary point, we find it like
Yeah,
that.
but it doesn't should be continuous in all the space. Only the vicinity you want to
Yeah,
to
just
analyze.
just in a small environment around the point you want to identify. Let's write it between definition. X0 is ordinary point, ta 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 ta. If for small enough epsilon, ta 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 ta. X0 minus epsilon, X0 plus epsilon. P and Q are there. If you want it really rigorous, I can do it more rigorous if you wish, but don't let me start with that. So now let's talk about regular singular points. What is that? Point ta 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 x0, but now we want that x minus x0 p of x and x minus x0 squared q of x will be analytical at a small environment around x0. Yeah, you just take the epsilon and play with that. And irregular singular point, just
Not one.
it is not ordinary point and not irregular singular point. So the first thing you do is check if P are continuous at x0 if you want to solve it around x0. The second thing okay, so if they are continuous, that is nice. Now you can just do Taylor expansion and find the exact solution around x0 if you need to, and you just want asymptotic behavior, you can take Taylor expansion of the P and Q around x0 and you will get very nice solutions, right? And now for regular singular point, okay, so if it's not analytical around x0, you check if that has the nice form, that it's similar to what's that name? Euler-Cauchy equation, equidimensional form, right? We did it for that were Cauchy equation. So what is the idea? Is now I can call, I can actually call Q and P, I can call P to be P tilde of x divided by x minus x0, and Q to be equal to Q tilde of x divided by x minus x0 squared, where Q tilde and P tilde are analytical everywhere in the small environment, right? Okay. And because of that, when you are really close to x0, it will have the form of what? Euler-Cauchy equation, right? Because for when x is approaching x0, that will be constant, and therefore it will be equidimensional. Everyone see that? Regular singular point is just when you cry. Okay? If you start crying, it's because it's regular singular point. Therefore, you don't have a recipe how to solve that, and you need to be smart, wise.
Or just given.
Yeah, or just being Kessler, he can just guess the solution. It will be, you can just give him equation, you look in that for a couple of seconds and then guess the solution. It's amazing.
Yes.
He's very impressive. Okay, so I will give you two options because I want to do that example, and if you will ask me, I will do the other example I have. But they're very similar, and that is very tedious. You want me to do one with repeated roots. Therefore, you will have to add ln of something, or one that don't have repeated roots, and we just solve regular repeated roots. Okay.
I want you to work out.
It just doesn't supposed to be hard. It's just very tedious.
Right.
So let's. By the way, I put all 9 steps of the solution to that thing in the Lambda. I have there 2 examples, and in your homeworks you have to do 3. Because if I had to write 2 solutions, you have to write 3 solutions. It's how it's works. Snell had to write 0 solution, I had to write 2 solutions, and you have to write 3 solutions. And איך אני אומר שרשרת המזון? Chain of food.
Food chain.
You know that, Dima?
Yeah. There is the predator. There is the super predator, the predator, and everyone else.
Great.
Okay. and
In the
start
prey,
to,
yes. Prey.
and start to worry that I gave you the exact same. No, that is not the exact same equation. Okay, that's
It's okay.
good.
It's
I
exactly-
thought for a second that I gave you the exact same equation that I'm supposed to do now, and then you have just the solution. And then we are equal, because
Equal
I had to
dimension.
solve 2 and you had to solve 2 and copy 1.
Equal dimension.
But it's not the case. Sorry. But it's actually a very nice case, because it's not around 0, it's around 1. It's the same thing, but it is nice because in a test you will not always get the classic presentation of the equation, and you will need to think a little bit and decide what happened here. So that is the equation. OD, students, now we know each other, we can start. We have that. Let's just put the coefficient of y2 primes to be 1. That is the first thing you do when you meet an OD, right? And then now we can talk about some explosive points that start to explode. What is the point that tend to explode? X equal with 1. Of course,
Gender equation.
now just defining P as x divided by 1 over x. Really? Got that? Okay. Okay. So now what we do, we take x minus 1, multiply it by p of x, and see when x approaches 1, will approach 1. Right? Everyone see that? Because then you will have just actually minus 1, right?
Right.
Because then it will be minus x, and x is approaching 1, so therefore it will be minus 1. Now we have q of x. It's just 1 over 1 minus x. Now doing this, but now with x minus 1 squared,
It will go to 0.
it will go to 0. Right. So is it regular singular point, ordinary point, or regular singular point? Yeah, because they are not analytically around 1. And they behave nicely like Euler-Cauchy equation, like the equidimensional equation. Okay? What is the next step? After identify that, do some Frobenius series. Right. So what we're doing is just
Expanding around.
yeah, let's do one thing before, because we really need to find some, how do we call that? We need to find if there is some degeneracy or something like that. That is not exactly degeneracy, but we need to see what to do with this stuff, so we can take appropriate form of the sum. Actually, now when I'm thinking about that, we can actually, because of what I showed you with x to the alpha plus r, so it's a little bit different. You assume there is a little bit difference between the solution, even if I will take it x to the r like that, I will get the same thing. Why? Because here, if I will assume there is a little bit of perturbation, I get the ln free. So I'm supposed to get that also from that equation, from just getting the recursive relation, and from the recursive relation I will get if there is any degeneracy in the characteristic polynomial, then I will get what I need. Right. Okay. So let's start. First, writing derivatives. I prime is just n plus r an x to the n plus r. Oh, by the way, no one caught me doing wrong stuff. That is very bad. We're not focused and we're not listening to me, because I'm supposed to write x minus 1 because we're doing some perturbation around 1. No, actually not
But
perturbation,
if you're doing
taking power.
perturbation around 1, then their convergent radius will be 0.
What?
If you're expanding around 1, then the convergence
No,
will be 0.
because Frobenius told us, okay, just multiply by that and you will get nice stuff. Because here you can catch the behavior of exploding. R can be, for example, negative, then you will have exploding term. Like equidimensional equations of these. Okay, x minus 1 to the
n plus r minus
n plus r minus 1. Okay. Let's take the second derivative. Oh, I hate that. And the worst part that I solved that already and I need to write that again. But okay, let's pretend like I'm happy, because we don't like to do things twice. Okay. For next tutorial will be much nicer, and then we will really start with the course, because now we just reminders from all the course. So I have nothing to do. Okay. So now just plug into the equation, and what we should get is let's switch boards. Our reading time actually good. By the way, I like sometimes to give the challenge. If someone interested, try to find, using the gamma function, the value of e to the minus x times ln x to the n dx. Try to use the gamma function to show that that is actually very nice. You have very nice trick to do that. So if you are bored, you can try to do that. Sometimes it appears in our course, and it will appear because the gamma function have a really interesting role in our course. We will see that. We actually have also incomplete gamma function in our course. So that's nice. The Kessler told us in the first lecture in math method, don't go to a blind date without a nasty function. You have to introduce yourself first, and then show to her your Bessel function. Because who don't like some אני אומר פונקציות מונפצות? You don't, okay. So, okay, let's focus on our case. We have just n equal to 0 minus n plus r, n plus r minus 1, a n x minus 1, n plus r minus 1. Plus, okay, what is x? X minus 1 plus 1. So let's write that first. We have that minus n plus r, a n x minus 1, n plus r minus 1. Then let's recall that I told you this thing just it will write y prime, but because you multiply by x, it's like multiplying by x minus 1 plus 1, right? Because it's the same as x. So you will get plus r.
So so there should not be minus 1 in the power.
No, because that is the 1.
Yes, but you're using y prime.
That is just y prime times x.
Okay.
X equal to plus 1. Okay? That is the x minus 1, that is 1. That will be that. That will be that.
Why did you put minus in the first term?
Because you have 1 minus x and not x minus 1, right? See that?
Ah, okay.
Yeah, no problem. And now, just add in the last term. I took that equation to give myself much short. Okay. And then just check in. Okay. We need to switch some indexes in two things, right? By the way, I have some anecdote. It's not written in my tutorials, but I will tell you that. We did something that's right here. Here I can do a lot of nasty stuff. If we have recursive relation that only depend on an and an plus 2. Okay, it's very easy because then that means you have two recursive relations that define two functions, right? With one constant that will be a0 and one constant that will be a1. But if you have equation of an plus 2 plus something an plus 1 plus stuff times an. One nice thing that you can do is actually the same idea that we did with the Fibonacci numbers. The exact same idea. Why? Someone know? You can assume that the nth derivative of a function times n factorial, because we did not, when we did that, we didn't divide by n factorial from Taylor expansion is the derivative of a function. It means assume that n factorial times I to the n equal to an. That is actually coming from Taylor expansion. Then you can actually, okay, maybe, no, you cannot find, okay, that, because that will be equal hardness to solve that. Let me think, because there are cases, okay, there are cases that you can neglect some terms and get from the recursive relation nicer things that will be negligible, and therefore when you switch in that, now you can take the differential form and find a nicer solution that approximates. So we're a little bit off because I thought that without any approximation we will get from the recursive relation other thing, but you will just get the equation. But you can do some neglect some terms and get approximation from that, and then you get the solution. I'm a little bit sick today, so I don't know if you see that, but it came. And what I got? 2 alarms.
Nice price.
Yeah, we're on the 5th floor, so I will be in shape by the end of the month. Okay, so now let's just rewrite the equation. N plus r plus 1, n plus r, a n plus 1, x minus 1, n plus r minus n plus r plus 1. Everyone know how to do that? I'm not doing it too quick.
You just redefine n.
Yeah, redefining n as n plus 1. Yes. Just look, here it starts from n equal to 0. Okay, here it's not obvious, but when you take the derivative, the first term is of y will not be equal to 0. Need to be careful. Wait, that is true. I can always switch. I think I need to get it out of the equation. Yeah, and from that I will get the characteristic equation and everything. So I will write it in the end. Okay, so right now, everything with that, n plus r, a n, x minus 1, plus r, minus a n, x minus 1, plus r, and then the 0 terms from here. So what we get is r times r minus 1 with a minus sign, x to x minus 1 to the r minus 1, right, times a 0 and from that I'm getting the exact same thing. Let's write it. Minus R A0 x minus 1 to the R minus 1. Right? Yes. And then we set everything to 0. Whew, really tedious. So what we get that every term of that will be equal to 0. From those stuff, we get R. From those guys, we will get recursion relation. Then we get recursion relation that depend on R, because R will have two options. Actually, in our case, it will have, I think, only one option, but we know what to do when there is two options, so we will get the solution. So let's write it. First, let's find R. Yeah, minus R squared plus R minus R equal to 0. And then you find actually edge case of Frobenius. That it's actually looking like a Taylor expansion, right? Because R we will get from that R equal to 0. But actually you have explosive term from the line. You have to have some something exploding there, right? So it's the line, but it's not looking like a Frobenius solution. Right? In Frobenius you get a term that is 1 over square root of x times Taylor series or something like that. But here you get actually a Taylor series plus ln times Taylor series. In a test to get that thing and to do everything around 1, it's pretty difficult in the test, right? You know all the stuff, but now you need to rely on your senses and the definitions and do new stuff. I have plenty more for those kind of questions. I will not be here, by the way. I don't know if I told you, but in the last 2 weeks I will not be here. I will be in the military, so someone will be here. I think if some of you know Eitan Grinzai, I will talk to him to be here instead of me. Okay? Now find R equal to 0. So we have one solution that we just need to multiply by line, and the other just as is. And we get one of the nicest thing we can see from here, that all the R can just throw away. Now it would be really nice. So let's switch boards. It took me, I think, half an hour to get the nice form of that OD. I tried to do something not around x0 equal to 0. Don't want x0 to equal to 0, but that is simple to do that thing. But to find something that will everything cancel and get like a textbook question that everything is nice, it's very hard. So all the other idea I kept for the homework, right? I'm joking. I took the other ideas from Bender's book. You can actually find 2 of the questions I provide you in the homework in Bender's book, and 1 I invent. Let's see if you can guess which one I invent and which one Bender do. So I get all the repeated roots, and let's look on that. Now we have n plus 1 times n a to the n plus 1 minus n plus 1 a n, and now what we have here is
Wait, n plus 1.
what? Found mistake?
It should have been a n plus 1
Where?
on the second term.
Yeah, preloaded one. I think he said it in words but didn't write it. But I'm not sure. Okay, so n plus 1 times n minus 1. Oh, by the way, I can have some mistakes in calculations, so tell me if you find something.
Really? Yes.
Alright.
Yes.
Because that is much nicer than my tutorial notes. So don't think that we're supposed to have.
And you have a degree of freedom in choosing a 1.
What?
You should have a degree of freedom choosing n equals 1 because you divided n minus 1 from both sides.
You say that n equal 1 will be a solution.
Unless you can't divide both sides.
No, you think. Let's see. No, I don't think the
Instead
problem.
of quadratic equation,
Let's
you got
let's
a
see.
linear
Wait,
equation.
we look at my tutorial notes because we're not supposed to happen. Yeah, that. Let's see. We're supposed to have n minus. N minus. N plus 1. Let's see. Here it's n plus 1, here it's n. Okay, so it's good. Right. Now. Not sure. Okay, I don't think I had a mistake in calculation here, but I'm not able to find it.
Yes, but now you have only one solution.
No, I don't have one solution, I have two solutions. Because I have one that I'm multiplying by ln, and one
okay.
that I'm multiplying by let's see, because from that is right. Go away, we're in the physics department. We can divide by 0. But what we get from here is
computer science.
a0 and factorial. But I'm trying to see that is just the Taylor series of e to the x, right? That means e to the x and ln x, e to the x supposed to be the solution. So let's plug them in. What were the equation? Minus 1 x minus 1 e 2 prime. What were here? Let's look. 2 and then plus y. Okay. Plus y equal to 0. Now we just, oh, no one finds that. That is the actual two solution. Here I can neglect the -1 because it's just a constant that multiplies the solution. But here, no, I can also. I didn't try to do that. Okay, so let's just plug it in. If it's plus x, no, it's not plus.
It should be plus.
If it is plus, it's still not right because
No, it
plus
should be
and
plus minus unless the e to the x solution does not work.
Yeah, and that's why I think there is a problem now. I see. So what is wrong here? Here it's minus
And plus.
and x and minus x, just minus x minus 1, and they put their plus. No, you put the -1 minus. Okay, and the last term is just plus y. And they got the right answer for the 0th term. So that is a little bit confusing. Why I got that? Okay, I don't see that, but that is the point that it's just a recursive relation. If you want, I can send a mail if the screenshot of the solution I already wrote here. I did the calculation, they're a little bit different, and I didn't got that. I got something else, but in the last couple of minutes I have for the tutorial, I want to talk about something that you should know and remember. That is product of numbers. I think you may develop it in the lecture. You find you saw that something similar. Let's say from n to capital N of alpha n plus beta. Let's just write it. We want to write it nicely with the gamma function. Have you saw something similar to that?
Yes.
Yes?
Not exactly this kind, but we
Yeah.
saw something similar.
Yeah.
So it should be.
So often when you are dealing with recursion relation,
It should be gamma.
you get in the recursion relation some product. Okay, let's say for our case, the general form is like alpha n plus beta an. Okay, let's write it with an minus 1. Now it's right. Okay, that is the general form. And we want to find the general formula for that. What we will do is, first thing, we just take alpha out of the equation, and then what we have is n plus, let's switch it to minus because it's much looking nicer, beta alpha.
No. N divided by alpha to the n minus n.
What? No.
Inside you have alpha n, but small n, and you put
I
out.
divide everything by alpha, right? I divide each term, I took alpha out,
Okay.
and then you have just the product of alpha and times,
Okay.
actually n plus 1 times, right? Because we start from 0. And now we are using the fact that the gamma function for all z, actually even for complex numbers, so it can appear in a test, for example, that you will have a product that also includes some complex numbers. So now you will know how to deal with that. Okay, so you have something like that, and you know that thing is just that. From that recursive equation. Okay. And what we know is the first, okay, we want it to be plus or minus, but I will take it to be plus. Again, on a second thought, it will look nicer. Okay, and now what we want to write is that thing. It looks similar to what? To gamma of n capital N plus beta divided by alpha plus 1. But there is only one thing that we need to be careful about. We should stop, therefore we should divide by something. The last term, for example, is beta of alpha plus 1 is just beta of alpha, what? Gamma of beta of alpha, right? And we don't want that. We want that stop, and that's it. It starts from that, you do the recursion, and you get to that thing. So the only thing we have to do, just divide by that.
Here, beta divided by alpha must not be a negative integer, right?
Yeah. If that is negative integer, you start to cry, or you just look on the incomplete gamma function. The incomplete gamma function is basically that thing when the integral starts from 0 to from s to infinity. It depends on two variables, and it's just x to the z minus 1 e to the minus x dx. It's nice thing, and then you need to work and be careful with that when s is close to be negative integer, but it will come later on in the course. You can actually prove with that if you know what is the Euler-Mascheroni. Everyone knows what is Euler-Mascheroni constant? Euler-Mascheroni constant is the limit of n to infinity of the, everyone familiar with the harmonic summation, right? 1 over n summation from n equal to 1 to n equal to capital N. Let's call it with n like that, minus ln n. It's a definition to be Euler-Mascheroni, and it's approximately 0.577. Okay? And it's appeared from, it's looking like it's appearing from nowhere, that the derivative of the gamma function at 1 is minus Euler-Mascheroni. That is very nice constant. By the way, we still don't know today if it's irrational or rational number. Mathematicians are pretty much dumb, and they didn't provide us with an answer to it. So that's why we're physicists. Okay, so just summarize, finish. We get that n plus beta divided by alpha plus 1 divided by beta. So that is a nice form to write some multiplication. Oh, by the way, have the alpha to the n plus 1. And just because I have time, let's solve that thing real quick. You have two methods of doing that. One is just looking on the gamma function and then to realize the solution. And one is really being okay. So what happened to the gamma function if I will take the derivative with respect to that? I will just have till to infinity ln of t to dz minus 1, right, e to the minus z. Wait, with respect, why you wrote there that? It's supposed to be t dz dt. And then, if I will just plug z to be 1, what I'm getting here? I'm getting that will be 0. Therefore, t to the power of 0 is 1. So, z equal to 1, we're getting that. Is that familiar? What? Yeah, it's actually the minus עולם השלומי constant. That is a nice way to write it also. But, okay. And look there, that is the exact same integral, but for n equal 1. What happened for, if we want the nth one, just take the derivative n time and you get that. It's a nice thing, why? From that you got what? The Taylor expansion of the gamma function. It's really nice. You have another way to do that, of just 0 to infinity, taking n to 0 to infinity. Maybe that will be more straightforward for you. If I will do that, take that to be e to the z minus 1 times ln t, and then take the Taylor expansion of that thing, and we get ln t to the n divided by n factorial ln z minus 1 to the n e to the minus t dt. Then just switch those things, and then we got actually the Taylor expansion of that, of the gamma function. It's really nice. Actually, didn't saw it in the internet. I will need that for one of the assignments they gave us last year. So you can see the assignment in this course can be really horrible or really fun. It depends on your personality. And then from what a mathematician would say, from the uniqueness of Taylor expansion, that is the coefficient here. Therefore, it's the dense derivative of the gamma function at 1, because it's the expansion around 1. And that is a nice form of that. Yeah, so we pretty much did everything I want. That thing, I can probably find the mistake of by just looking here, but I don't feel in the point of doing that because, okay, we will find the recursion relation, we will use things like that, and it's pretty much the same from ODE. Next tutorials will be less technical and less, it will be technical, but you have some point of art. Here is just following a recipe. You will have to neglect the right terms and to really think about that and have some sense of intuition to that. Here you're just doing, you just punch the equation until it's solved. So you have another example in the tutorial notes if you need, and I already uploaded the homeworks. One last thing, do you want me to clear out what to do in the numerics in the homework? Or everyone?
No, maybe it's a good idea because not everyone took the
What?
Yeah, I actually did.
No. It just ask ChatGPT. It will provide you with the right answer, and
You just need to write code that solves numerically the equation and plot on the same plot. Once the numeric solution and once your solution with the same initial condition.
there is a package in Python that do that. Kalinsky told me, and what I did last year, because I also didn't do numerics. I just read about Ranch-Kuta and inverse Ranch-Kuta. It's really nice methods of solving differential equation.
Which you don't really need.
And then you just ask ChatGPT provide me with a code that do that, and a solution. You want the solution to look something like that. Okay, I don't care which way you do it with numerics. Do something you can choose. It's need to validate that your solution is right. I don't care how. Here is one option that I did last year, but there is many options. Okay.
You can use Python libraries that doesn't even tell you.
No, I mean just the output that I want to see.
Should be two graphs. One.
You have.
One.
Let's see. I have another. Let's take the purple. Okay. So you will have here, for example, a numerical and blue. I'm not colorblind, so it's fine to do it with different color, or you can do it with dash line or star line with a lot of stars. It's also nice. And theoretical graph. Let's write it like that.
We must calculate the constants analytically.
Yeah.
Otherwise, you can't plot.
Analytically. Yes, sometimes you need to use, you can only provide a solution that will look like that, and you need to solve an equation of in some sort looking like that. That is general expression of a function that depends on y and y of x, and you need to get y of x and match it. But you can't do that, obviously, right? For every f. You agree with me? For example, if I will give you y plus e to the y equal to x, it's impossible. If that is the solution you got, you know you get sometimes things like that in ODEs. You have to use, for example, Newton-Raphson or something like that numerically that you know it's right to find each point the solution that will be here for you if you want to use MATLAB or something like that you have experience with. There is a function that's called F0, I think, that will provide you with that thing, and you just take array theoretical function and plot it here. And for example, it will look like that. You can do it without the dash line and show that the numerics have pretty much the same behavior.
It should be one on another.
Yeah, but
You can't really
sometimes
see
when you're doing asymptotically, it's also fine that your graphs will look like that, because it's up to a constant or up to another order that, okay, maybe you need to take another order.
But not for the first take, for the first assignment, because all the equations are solved analytically.
Yeah.
So it should be one on the other.
By the way, you need to specify your initial conditions. You need to say, you need to set, for example, y0 to be whatever you want and y prime to be whatever you want. Don't take a degenerate case that will provide you with the zero function of something or something like that, just to show me. You see, that is a nice function. Okay.
One on another.
What?
One on another.
Yeah. Okay, so we finished? Why? Even the zero function can sometimes prove that is a solution, because the computer don't have it doesn't calculate it to the exact number, so it will always have some fluctuations. Okay.
Can I ask you something?
Yeah.
ביי ירדן, תודה.
ביי, בכיף. סליחה, אני קצת חולה היום, אז... בסדר.
היום? ואני לא מצד השני.
ביי יוסף.
ביי.
זה השותף של מנואל, נכון?
נכון.
זהו, ידעתי שאני זה אותו איפשהו.
כן. זה... קיבלתי? לא. זה הסעיף ב'.
Dima, by the way, if you still didn't solve
Yeah, I have a
the
couple of
question.
questions. I'll be in a minute.
So let me just see, because
Sure.
I
You have yeah, I get you. Okay, so this is the second safe bet, right? I received this second order differential equation,
right.
and now I don't know how to
You
get.
prefer English or?
I prefer English.
Yeah, okay. Yeah, it's okay. It's okay. I didn't remember what is
Sure, if you want Spanish.
Yeah, I remember you and Manuel talking Spanish.
Right.
Yeah. Okay, now you're stuck.
Yeah.
Because you don't find the solution. The trick here, do you have the pen for that?
Yeah.
Or I will. The trick here is actually realize that you already have the homogeneous solution to the first equation, and therefore you have the solution to that equation. Because where that equation came from?
From the
Original equation.
Yeah.
So you just take yi when I is in the order set 1 to 3, right?
Yeah.
Equal to L of x times y3, right?
Right.
yi divided by y3 equal to L of x.
Right.
And then you get from that, by just taking the derivative, you get L of x solution, general solution, right? We look in the form of d to dx of y of 3 y by yi, right? And then you have the solution.
No, how?
That is very nice.
Okay, so you have that this is a solution for the
Yeah.
homogeneous.
And look, that is second order differential equation. So you could not have more than two solution in two independent solution. So what is the
right? So
why you have only two? Because when I equal to 3, that is 1, and therefore the derivative is 0. So it's obviously not a solution. It's a solution, but it became 0.
right, everything
Yeah.
is linearly independent from.
Yeah.
Right.
Yeah, that is the nice thing. That's how it's not contradict, because if not, you just have 3 solutions.
And it would contradict the assumption
Yeah.
that it's a second order.
Yeah,
differential
and
equation.
now it will be a problem, but now you find the solution. But if you have the solution, you have everything you need.
Right, okay. Right.
That is very nice, very nice thing. I thought about save it to exam or something like that, but I said, okay, it's just the first thing you could give that to in ODE class,
And you could get
yeah. We don't have. That is not a good question for
an example.
exam in our course, but in ODE it's a very nice question.
Right.
Yeah, but that is a trick. I try to give a hint without
Giving it.
giving the
Here, right? What you
Yeah.
said.
hint. You already have a solution to the other ODE. It is recommended to use it.
Right.
That is the best I could to do without just telling you, look, that is your solution.
that.
Explain why.
Right. Of course. Sure. Thank you.
Yeah. Okay.
One last thing. Okay,
Equation
so-
2.
No, I have like this is my solution. You want me here? I just need to. Can I express it like this and just put you both equations in the graph?
Just put the graph like I showed here,
That
with the
it's
numerical stuff and all of those stuff that will look, those functions will look the same, and then you will say, look, there is nice graph, I'm right, like every theorist, because everyone here is a smart physicist because it choose theory instead of experiment.
Actually, I did it about numerics. You can use symbol calculations. There is a SumPy library in Python, so actually you can substitute your solution in the equation, and Python, this package, do like some.
All the things you need and simplify and see if
Yes,
it's 0.
yes.
But no, that is not valid for our course. Okay, of course, here it's fine because you have the exact solution. In next exercises, you will have something that's asymptotically right, but not right, not actually right. And then the graph will look something like that,
Yeah.
or maybe closer, and then you will not be
I
able
mean,
to.
for the first task, it's okay.
For the first task, it's
I mean,
okay.
for
I
first
prefer this thing, but if you just given me a picture of the Python, say okay, it's equal to 0,
Yeah,
I will believe
have
you.
it.
And if you already did that,
I
that
did
is
it.
okay. Yeah, don't tell Kalinsky because I told him it's not okay.
Okay.
But now we are in record, so we can see that.
He can
Yeah, possibly.
shout at you.
Okay,
Thank you.
that's it.
That's all.
And
Basically, I have the same questions.
you saw what?
I get this equation, but
Mhm.
I have no idea how to.
Yusuf, let's see you.
let's
I
say
explained to you, now you need to explain to Dima. In Spanish. No, no. Do you know Spanish?
No.
Not yet. Give him 1 month and then he will know Spanish.
Okay, so the idea is that since we know that y3 is a solution of this equation, so now what we can the other equation came from that. Do you read the second order equation? This that you got. Okay. You have it slightly different than I have.
I divided both parts by.
Okay. By y3
is the same.
I did that as well.
Yeah, but actually, you know the thing that is interesting here, that you don't even need that thing to see that.
Right.
Even if I will tell you, okay, do that substitution and find the solution, you will not need that. How do I explain that? You don't need the actual equation to find the solution. From here to find the solution, it will be horrible. Don't try to do that. I promise you it will be horrible. But doing it from what we already have is very nice. Okay, continue with that.
So we want to generate how many functions? Since it's second order, we want to generate 2 homogeneous, right? Okay, so the idea is that we are going to say that our solutions are we got into the previous in the previous exercise, right? Which was taking y3 to be Lx, right? Okay. And we know that yx is a solution. So from here, we just have this relation. Okay. And the idea is to divide from both sides. And when we divide from both sides, we have L of x, which is a solution of this equation. It will be the derivative of these two, right?
Okay.
And this will give you 2 functions. Why?
We have so we said that
yi. You need the
yi, the index.
You need the solution. Yeah.
this.
This is a solution, right?
By
So
solution.
We
Okay.
know it from what? Why we said that this is the solution? We don't know, right? Only what we know is that this is solution of
That is y. And you know it's a solution to the original ODE.
this one.
Yeah, that makes sense. Okay. You have the original ODE, right?
Yes.
Y 3 primes plus f1 of x, y 2 primes plus f2, y prime of x plus f3 of x, y equals to 0. You have 3 solutions, y 1, 2, 3. Now you did the substitution of y equal to L of x times y3 when L of x I already did all the thoughts behind to give you the substitution and all of those stuff, and you did get that. I told you x to that, x def prime. Okay. Right? So you get the second order differential equation. Right? And now what we are trying to say is you have the solution to that. So you have the solution to L of x. Because you know the solution can have two forms. Forms of y, it will be y prime, y1, y2, y3. And in the form of L, you can provide the L that will solve that equation after the substitution, right? No? Okay. We'll try to be...
So after substitution, I'll have another differential equation, which is second order, not the
yeah,
third
but
order.
we know now we have yi. It's a solution, right? To the differential equation.
The new one?
We want to
No,
find-
to the original one. Right? The original one and the new one has this actually some sort of the same solutions. Because one is you need to find the L that will provide you with the right y to solve that function, that ODE. And the other one, the other way to look on that is to provide the y that will give you that when you can get that L of x from dividing by y3 and take the derivative of capital L is just that form of that. And that will provide you if you will do that substitution to the original equation, okay, you will get back that equation.
Right.
So choosing the right y that is a solution to that will be also a solution to your equation.
Ah, you mean that
Yeah.
I can pick
It's
y1,
if and only
y2.
if. Yeah, you have
Ah.
two functions. If you choose the right function here, you have a solution to one equation and the other equation. But one equation is much easier because it's second order. Even so, it looks horrible, but don't think about that. Believe me, it's horrible. And therefore you have, okay, now you have that thing, so it's nice.
So now we have two solutions, right?
Yeah, why you have only two solutions? Because I can provide you with three good y's that will work here. So how and your equation on L, small l, is second order. How it's not contradict the assumption that this is second order differential equation? Why there is no problem here? Because I can provide you with three right L's. Okay, they have to depend on each other, right? Because I can't have three unique solutions. But you will ask me, okay, what the hell? Which one is which one I can throw? Because I can substitute y1, y2, and y3. But what happens when you substitute y3?
It's a zero.
Yeah, so it's also a solution because it's homogeneous, but it doesn't provide you with anything, so you just throw it away.
It's useful.
It's
useless.
Useless. Yeah.
So we just have to put the solution in terms of y1 and y2.
Yeah, you can leave it like that. And then just plug it into the variation method and then you're fine.
And that's the answer to the third.
Yeah, and that is the answer to that equation, to that question. I think it has its own charm, I will say it like that, but it's not an easy question. That's why I say the equivalent to 5 questions.
Right.
I said, okay, they are just the technique. If you understand that thing, you understand how to solve everything with the variation method. I actually thought about just giving you that. You have 3 solutions. Good luck. But I said, okay. It's already it's already hard. So
Let's do it. Yeah, easy.
yeah. I understand that not everyone did advanced course in OD as an undergrad.
Right.
I studied it in the original OD. It's called reduction of order. You maybe remember it.
Yeah.
Yeah, sure.
But to after that many years to do that thing, and you just get ODE that depends on capital L prime, so just put the integral and it will look nicer.
Right.
It will simplify the students' lives of it. I think it simplifies.
Yeah, a lot.
Yeah. I think it's a nice question, though it looks horrible. I know people that did 8. They told me probably 3 of the 8 are not right because they gave hard questions. I don't
Which
know.
ones were hard?
I don't know.
I don't know. They said the second one.
The second one is actually very hard because it involves physics in it. Because you need, it's looking like x squared.
I saw it was like a Hermite polynomial, something like that.
Yeah, it looks similar to that. Exactly. It came from there. So one way is just, we meet polynomials. I'm cool, and then just okay.
I'm cool and lazy.
Yeah, and you probably. So if you did okay. Actually, at the start there were -9, and you need to do the Fourier transformation of that OD, and then you get that meet.
Right.
Because I didn't want it to be that obvious, but then I realized, oh my God, it's way too hard. Don't do Fourier transform and convert it back to find the solution, and don't guess a hilarious form of a solution. So and someone sent me an mail. You can just put plus here, and it will be much nicer. And it's actually the Fourier transform equation. If there is minus here, you will, after doing Fourier transformation, you will get that. Actually, so it's actually providing nicer form. And the thing here, why I say it's like doing quantum mechanics again, is because x squared here, you will call that your energy, and you will call that the potential. What is the potential of x squared?
Harmonic oscillator.
Harmonic oscillator, of course. And then what is the, how that's called? Like in waves, that you have some form of the waves, and then you have a lot of shenanigans under it.
The wave function.
Something like edge of the function, something that multiply the function. That you can see here, you have that thing.
Small function and fast
Yeah.
function.
Yeah, exactly. So you know the boundary function, I will call it like that, is supposed to be some sort of Gaussian. So you guess a solution like that. That is the catch of that thing. Or just here you have, I gave you already e to the minus x or e to the x squared to let you know Gaussian or Hermite polynomials. Think about something that actually, given it non-homogeneous, were actually some sort of a hint. So after plugging that and realize that c equal to minus 1 over 2 or 1 over 2, I don't remember, you get the equation by 2 primes equal to 0 or something like that. You can see from here. What is that? You will just you see that?
It's derivative
If you will
from,
multiply everything by e to the x squared over 2, e to the x squared over 2, and here e to the x squared over 2, e to the x squared over 2. That is just the second derivative of e to the x squared over 2.
Whenever you don't
That-
know what to, whenever
That
you
is just y times e to the x squared over 2. So let's call it w. Okay? And here you will have the derivative of e to the x squared over 2 times x. That is exactly the derivative of that, right?
right.
You're with me, Dima?
Yeah.
And the derivative of y. And here you have the derivative twice of that thing, and everything just collapses into a nice form. Yeah, I think that were the trick.
Whenever you don't know,
An answer to a question in ODE, you just need to say it's the integrating factor.
Yeah, so I chose that equation because I said, okay, come on, they're not mathematicians, they're physicists. They will try to use their intuition, but then I realized that no one tried to use the intuition and tried to do the red